So basically, this talk is going to be about the Brazil-Nuremberg problem for the p-Laplacian. So here's the problem that you're going to look at. This delta p is the p-Laplacian, and you have this critical power p star and a positive parameter lambda. So when p is equal to 2, this is the classical Brazil-Nuremberg problem, which has been studied extensively, beginning with the 1983 paper of Brazil and Nuremberg. So let me first recall some multiple p equal to 2. When p is equal to 2 and n is bigger than or equal to 7, this problem has infinitely many solutions for all positive lambda. This is a result of De Villanova and Solimini in 2002. So n bigger than or equal to 7 is what's called the high dimension, and less than or equal to 6 is called the low dimension. So this is the high dimensional case where you have infinitely many solutions for all positive lambda. Now let's look at what's known in the low dimensional case in between 4 and 6, and we're still looking at the semilinear case p equals 2. First, let's consider the case where lambda is not an eigenvalue of the negative Laplacian with zero boundary data. Then if lambda is smaller than the first eigenvalue, it's known that this problem has n plus 2 over 2 distinct pairs of non-trivial solutions. This result is due to De Villanova and Solimini in 2003 and Clapp and Weth in 2005. So Clapp and Weth point out that there was a small gap in the paper of De Villanova and Solimini, and Clapp and Weth basically fill that gap and give a different proof of this multiplicity result. And Clapp and Weth also proved that if lambda bigger than lambda 1 is not an eigenvalue, then this problem has n plus 1 over 2 distinct pairs of non-trivial solutions. So essentially these multiplicity results for n between 4 and 6 are due to Clapp and Weth. So now let's look at the case where p is 2 and lambda is an eigenvalue. So here's what's known. Again, Clapp and Weth showed that if n is equal to 4 and lambda bigger than or equal to lambda 1 is an eigenvalue of multiplicity m, then the problem has n minus m plus 1 divided by 2 distinct pairs of non-trivial solutions. This was still proved in 2005. And then actually their result also applied for n equal to 5 and 6. But for n equal to 5 and 6, now there is a better result due to Chen, Xiuji, and Zhao. So they proved in 2012 that if n is 5 or 6 and lambda is bigger than or equal to lambda 1, then this problem has n plus 1 over 2 pairs of distinct non-trivial solutions. So the result of Chen, Xiuji, and Zhao apply whether or not lambda is an eigenvalue. So you see that the number of pairs of non-trivial solutions that they get does not depend on the multiplicity of the eigenvalue lambda when it is an eigenvalue. On the other hand, the result of Clapp and Weth depended on the multiplicity of the eigenvalue. So there's an improvement in the result of Chen, Xiuji, and Zhao. So this talk, okay. So that's basically for the semilinear case where p is equal to 2. In the general case where p is between 1 and n, there are some similar results. So the first result is due to Cao, Peng, and Yang. In 2012, they showed that if n is bigger than p squared plus p, then the problem has infinitely many solutions for all positive lambda. Notice that when p is equal to 2, p squared plus p is 6. So this is saying that if n is bigger than or equal to 7, then you have infinitely many solutions for all positive lambda. So this corresponds to the result of the De Villanova and Solimini in 2003 for p equal to 2. And here's what's known when n is between p squared and p squared plus p. Again, notice that if p is equal to 2, this is saying that n is between 4 and 6. But now we are looking at the general case where p is between 1 and n. And if n is between p squared and p squared plus p, and lambda is smaller than the smallest eigenvalue, then he and Zhang showed in 2020 that this problem has infinitely many solutions. But their proof applies only to the case where lambda is smaller than lambda 1. So here's what the main results that I'm going to present in this talk today. So basically, we are going to prove some multiplicity results for the case where n is between p squared and p squared plus p, and lambda bigger than or equal to lambda 1. So this will complement the known results, and our results will be similar to those of Clapp and Weth and Chen, Xiu, Jin, Zhao. Now, the proofs in the papers of Clapp and Weth and Chen, Xiu, Jin, Zhao are based on two things. First of all, they use the relative equivariant Leuchter-Schneider category and the Krasnoselski's genus, and their proofs make essential use of the fact that the Laplacian is a linear operator, and so it has linear eigenspaces. Now, for the p-Laplacian is not a linear operator, so it does not have linear eigenspaces. So their arguments cannot be extended to the p-Laplacian. So we need some new techniques to handle the p-Laplacian case. So our proofs will basically use some new abstract critical point theorems based on the Z2 cohomological index, and this abstract result does not have any assumptions involving linear subspaces. So it does apply to the p-Laplacian that does not have linear eigenspaces, and of course this is also of independent interest. So to state our results, let me first recall some things about the eigenvalue problem for the p-Laplacian. So this is the eigenvalue problem for the p-Laplacian. The eigenvalues coincide with the critical values of this functional psi defined on the unit sphere in W1P0 of omega. And one can define an increasing and unbounded sequence of eigenvalues of this problem using a minimax argument. And the standard way of doing this is to use the Krasnoselski genus. But if you use the eigenvalues defined using the genus, we are not able to prove our multiplicity results because the eigenvalues defined using the genus does not have certain properties that we need to apply our abstract results. So what we are going to do is to use a sequence of eigenvalues that's defined using the Z2 cohomological index of Fadel and Rabinowitz. So here's the minimax scheme. So denoted by F, the class of symmetric subsets of the unit sphere, and by IM, the index of the set M, and then you take the class of such sets with index bigger than or equal to k, and you do min-max over that class, and this defines an increasing and unbounded sequence of eigenvalues, and we will make use of this particular sequence to state our theorems and as well as to prove them. And these eigenvalues based on the cohomological index were introduced in this 2003 paper in topological methods in nonlinear analysis. Okay, so to state our multiplicity results, first recall that the solutions of our problem coincide with the critical points of this energy functional E of U defined on the Sobolev space W1 P0 omega. And let me also denote by S of NP the best Sobolev constant. So this is the best constant for the embedding of W1 P0 omega in LP star of omega. So with this notation, now I can state our main results. So here's our first multiplicity result. So assume that n is bigger than or equal to p squared. So this basically corresponds to the case where n is bigger than or equal to 4 when p is equal to 2. So first of all, if lambda is not an eigenvalue that was defined using the Z2 cohomological index, then this problem has n over 2 distinct pairs of non-trivial solutions. Notice that this does not say that lambda cannot be an eigenvalue. It says that lambda cannot be an eigenvalue from the sequence that we just defined. One of the open problems about the p-Laplacian is that the entire spectrum of the p-Laplacian is not known. You can define various sequences of eigenvalues using different kinds of minimax schemes, but it's not known if any of those give you a complete list of the eigenvalues. So the part one of the theorem says that as long as lambda is not an eigenvalue from this particular sequence defined using the Z2 cohomological index, then the problem has n divided by 2 distinct pairs of non-trivial solutions. So this is the case where lambda is not an eigenvalue. And parts 2 and 3 concern the case where it is an eigenvalue. So first, suppose that lambda is the first eigenvalue, lambda 1, and n is at least 3. Then this problem has n minus 1 divided by 2 distinct pairs of non-trivial solutions. And finally, suppose lambda is one of the higher eigenvalues of multiplicity m. So suppose lambda is between lambda k minus m and lambda k plus 1, and that it's equal to this eigenvalue lambda k that has multiplicity m. And assume that this k is bigger than m, and m is bigger than or equal to 1, and that n is bigger than or equal to m plus 2. Then the conclusion is that this problem has n minus m divided by 2 pairs of non-trivial solutions. And all these solutions have energies between 0 and this level, 2 divided by n, Sn p to the n over p. And recall that the threshold for compactness for this problem is 1 over n Sn p to the n over p. So this right hand side is twice the threshold for compactness. So so we are not getting these solutions all below the threshold for compactness, but they can be up to twice that threshold. So that's the first theorem, and here's the second theorem. So this is assuming a stronger condition on n. Suppose n squared divided by n plus 1 is bigger than p squared, and so if p is equal to 2, this basically says that n has to be bigger than or equal to 5. So yeah, and then the conclusion is that the problem has n over 2 distinct pairs of non-trivial solutions with the energies in the same range. And this holds for all positive lambda. So this holds whether or not lambda is an eigenvalue. And notice that this theorem does not make any references to the spectrum at all. If this first inequality, n squared over n plus 1 bigger than p squared, is satisfied, then the problem has n over 2 distinct pairs of non-trivial solutions for all positive lambda. So these two theorems are our main results. And in the remaining time, I will try to outline the proofs. So the main difficulty with this problem is a lack of compactness. Usually with any type of critical growth problem, the PSC condition does not hold for all C. But we are going to show that this problem actually has some weaker compactness properties, and we are going to exploit those weaker compactness properties to prove our theorem. So what we are going to do is we are first going to prove some abstract critical point theorems that only assume these weaker compactness conditions, and then we will apply them to prove our theorems. So to state our abstract results, let me first introduce some notation. So suppose D is a Banach space and W is a closed linear subspace of D, and for a subset A of D, we will denote by the delta neighborhood of A in W, and we will denote by S the unit sphere in W, and by pi the radial projection onto the unit sphere, and finally we'll denote by Sn the unit sphere in Rn plus 1. And now suppose you have an even C1 functional on W with E of 0 equal to 0, and we'll denote by K sub C the set of critical points of E at the level C. So the main assumption here about E is that it's an even functional. So you have symmetry of U equals negative E of U. I'm sorry, E of U equals E of negative U for all U. And here's what we are going to assume for compactness. We are not going to directly assume that E satisfies the PSC condition for all C, but we'll assume these two compactness type conditions. The first one says that there is a certain threshold level C star below which the functional has compactness. So E satisfies the PSC condition for all C smaller than some C star. And the second condition, C2, is that there is some B bigger than C star, such that if you pick any C between C star and B, there is a set MC that does not contain the origin, satisfying the following two conditions. The first condition says that if you take any PSC sequence UN, either it has a subsequence that converges strongly to a critical point in KC, or it has a subsequence that converges weakly to a point in a critical point in case C minus C star, and it satisfies one of the following two conditions. Either the distance from un to mc goes to 0, or the distance from un to negative mc goes to 0. So this is basically an alternative. It says that if you take any PSC sequence, and if it does not have a strongly convergent subsequence, then it has a weakly convergent subsequence that converges to a critical point, but at a different level, namely at the level C minus C star. And it also has satisfies one of these two limits. And the second condition is that there is some delta neighborhood of MC and a delta neighborhood of negative MC that are disjoint. If as long as delta is sufficiently small. In other words, this MC and negative MC can be separated by delta neighborhoods if delta is small enough. So this is basically what we are going to replace the PSC condition with. So this is weaker than the PSC condition, but what we found was that you can work out many of the things in critical point theory that classically assume the PSC condition by replacing the PSC condition with these weaker conditions. So here is here's the abstract critical point theorem that we prove to get our multiplicity results. So assume that these two compactness conditions C1 and C2 are satisfied, and assume that you have two symmetric subsets B0 and C0 of the unit sphere with the following properties. C0 is compact, B0 is closed, the index of C0 is at least k minus m, the index of the complement of B0 in the unit sphere is at most k, and also assume that there is an odd continuous map phi from the unit sphere in Rn plus 1 to the complement of C0 in S, and then for some n bigger than or equal to n plus 2, and assume that you also have two numbers, big R and small r, both positive, such that if you define sets A0, A, B, and X this way, you have these inequalities. So what is A0? Well, if A0 is basically the image of the map phi, if your C0 is empty. If C0 is non-empty, A0 is basically the following set. What you do is you take all line segments joining points in C0 to points in the image of S of phi. So this 1 minus TV plus TV, TW for T between 0 and 1 is basically the line segment joining V to W. So you're looking at all line segments joining points in C0 to points in phi of Sn, and then project those line segments on the unit sphere. This pi is the radial projection on S. So you're taking the projections of all those line segments on the unit sphere in your Banach space W. So that's A0. And then A is basically just capital R times A0. So it's just a dilation of A0. So is B, but B is just little r times B0. And finally, this X is the set of points joining the origin to points. So X is a set of line segments joining points in A to the origin. So with these sets, define, assume that E is less than or equal to 0 on A, and and E is uniformly positive on B, and on X, E is uniformly smaller than B. Remember that this B is the B that appears in the condition C2. Then the conclusion is that this functional E has n minus m over 2 distinct pairs of critical points at levels between 0 and B. So in the classical case, if you assume that you have the PS condition under assumptions like the ones in this theorem, you get n minus m distinct pairs of critical points. So here we get something weaker. We only get half of those critical points. We don't get n minus m distinct pairs of critical points. We only get n minus m over 2 distinct pairs of critical points. So that's the price we pay for weakening the compactness assumptions. So if you replace the PSC condition with C1 and C2, you get about half of the critical points that you get in the classical results. So basically we are going to apply this result to get our multiplicity results. So but we will do this basically in an abstract setting that generalizes the p-Laplacian. So to state this the abstract results, suppose W is a uniformly convex Banach space, and suppose this W star is its dual space, and we will look at an operator equation involving so-called potential operators. So a continuous mapping from W to its dual is a potential operator if it's the Fréchet derivative of some C1 functional, capital F, on W. So consider the following nonlinear operator equation. Suppose you have this equation in the dual W star, and this AP, BP, and F are continuous potential operators, and lambda is a parameter. Here's what we are going to assume about these operators. So AP is assumed to be p minus 1 homogeneous and odd for some p between 1 and infinity, and it's also assumed that this AP satisfies a Holder type inequality. So this A2 is the Holder type inequality that we are going to assume, and both of these assumptions are satisfied by the ordinary p-Laplacian operator. So this is something that generalizes the p-Laplacian. And here's what we assume about the operators B and F. BP is also assumed to be p minus 1 homogeneous and odd. So and it's assumed to be positive for, and this is assumed to be strictly positive. And also we assume that it satisfies a Holder type inequality. And finally, we assume that BP is a compact operator. So in our setting, this BP corresponds to the term u to the p minus 1. So going back to the original problem, the Bressis-Nierenberg problem for the p-Laplacian, this BP is the term mod u to the p minus 2u. And finally, the nonlinearity of u is basically our critical term. So it's assumed to be a potential operator. The potential satisfies f of 0 equals 0, and it's of higher order than p near 0, and it's of higher order than p at infinity also. And we are assuming that this second limit holds uniformly on compact subsets of W minus 0. So this capital F is basically the term, is the integral of mod u to the p star in our problem. And then the solutions of this equation coincide with critical points of this C1 functional. You can explicitly write down what the potentials for AP and BP are, and this is the variational function associated with this operator equation. And again, if you look at the asymptotic eigenvalue problem for namely the problem APU equals lambda DPU, the eigenvalues coincide with the critical values of this functional psi defined on the unit sphere in W. And again, we can define a sequence of eigenvalues using the cohomological index, using the same minimax scheme that we used for the p-Laplacian. So suppose you define the eigenvalues lambda k using this min-max formula, and let me denote by this psi super A the sublevel sets of psi, and psi sub A the superlevel sets of psi. And one of the properties of the eigenvalues defined using the cohomological index is that you can compute the index of a sublevel set or a superlevel set depending on where your lambda is with respect to the eigenvalues lambda k. So we have these inequalities, namely that the index of the complement of the set of points where psi is bigger than or equal to lambda k plus 1 is less than or equal to k, and the index of the set where psi is less than or equal to lambda k is at least k. Okay, so here's our abstract multiplicity result for this class of operator equations. So assume that that we have the assumptions that we just stated for the operators A, B, and F, and also assume that E satisfies these the weaker compactness conditions C1 and C2. And suppose lambda is smaller than lambda k plus 1, and there is a compact symmetric subset C0 of the unit sphere with index at least k minus m, and there is an odd continuous map phi from the unit sphere in Rn plus 1 to the complement of C0, where n is bigger than or equal to m plus 2, such that we have these two inequalities. So the first inequality says that if C0 is empty, then when you look at the supremum of E on all line segments passing through points on the image of phi, that's smaller than B. Remember that this B is the number that appears in the compactness condition C2. And if C0 is non-empty, take the set of all line segments through points in C0 and phi of Sn, and take the supremum of E on those line segments, and that's assumed to be smaller than B. Then the conclusion is that our operator equation has n minus m over 2 distinct pairs of non-trivial solutions with energies between 0 and B. And again, this is in the classical setting. If you replace C1 and C2 with the Palais-Snell condition, the conclusion is that you get n minus m distinct pairs of non-trivial solutions. But here we get only half of those because you are assuming only C1 and C2. So let me just outline how this is proved. The proof is based on the pseudo index related to the cohomological index. So here's the definition of the I'm sorry. Here's the definition of the pseudo index. So this is basically something that's defined on the class of symmetric subsets of our one-axis space W, and then you have this set M. In our case, is actually the unit sphere, and you look at this group of odd homeomorphisms of W that are the identity outside the set where E is between 0 and B. So if E is less than or equal to 0 or E is bigger than or equal to B, then on that set, this gamma, you're looking at homeomorphisms, and then the pseudo index is defined to be the index of this gamma of A intersection M, where gamma ranges over our group of homeomorphisms, capital gamma. Okay, so this is a definition given by Benchy, but in Benchy's definition, he used the Krasnodębski genus instead of the cohomological index. But you could do pretty much everything that Bench did with the Krasnodębski genus by replacing it with the cohomological index. So that's what we are doing. So, and then you define these min-max classes based on the pseudo index. So you take the class of all compact subsets with the pseudo index bigger than or equal to some integer k, and you do min-max over that class of subsets. And then the theorem and our multiplicity result here is that suppose E satisfies C1 and C2, and suppose L of these min-max levels are between 0 and B. And again, B is the number that appears in C2. And then the conclusion is that then he has L-1 or 2 distinct pairs of critical points at levels between 0 and B. Again, this is if you assume the PS condition instead of C1 and C2, this is a classical result. In fact, in that case, you get L-1 distinct, in fact, you get L distinct pairs of critical points in that case. But here, since you're only assuming C1 and C2 instead of the PSC condition, we get about half of those critical points. And the proof of this is basically a matter of adapting the arguments that usually use the PS condition to use the conditions C1 and C2. So here, in particular, here is a deformation lemma that only assumes C2. So I just wanted to compare this with the classical deformation lemma. And you see that we are assuming that we are working with a level C between the threshold C star for compactness and the level B that appears in the condition C2. And this capital V is the set of critical points at the level C, together with the sets MC and negative MC. And then the conclusion is that we get a flow, just like in the classical deformation lemma. So the flow starts with the identity, and it's an odd flow at all times. And it's the identity if E is between the level C minus 2 epsilon and C plus 2 epsilon, but away from this set B. So in the classical result, this set B is just the set of critical points at the level C, KC. So you don't have MC and negative MC in the classical result, but the difference here is that the item 3 is weaker than the classical result. You don't have eta to be the identity away from KC, but you have to stay away from the sets MC and negative MC as well. And the rest are pretty much the same as in the classical result. And again, you can start from the sublevel set EC plus epsilon, and you can move down to the sublevel set EC minus epsilon, but only away from some neighborhood of this set B. So you cannot do this deformation staying away from the critical points only. You also have to stay away from sets MC and negative MC. And you show that just like in the classical case, when you do this min-max, if you assume C1 and C2, and if two of these min-max levels defined using the Suri index are the same, then you have infinitely many critical points at that level. And let me skip that. Okay, so let me just indicate how these abstract results are applied in the case of the p-Laplacian. So in the case of the p-Laplacian, the functional E is this functional defined on W1 P0 omega. And if you look at the asymptotic equation, where you set lambda equal to 0, if you look at that equation in Rn, its solutions coincide with critical points of this functional defined on D1 PRN. And so here's the threshold level C star. In our case, this is a well-known threshold level. It's 1 over n times the Sobolev constant to the power n over p. And what we need to use to prove to verify the assumption C1 and C2 is this global compactness result. So this global compactness result stated here is essentially due to a Mercari and Willem, and we made some minor adjustments there. So let me describe the set MC for this problem. So denote by U epsilon y the family of Cavendish functions where the best Sobolev constant is attained, and they are normalized in this fashion. And then our set denoted by M, the family of these functionals, or all positive epsilon and y in Rn. And then we can prove the following theorem. So the theorem basically implies that the functional E satisfies the weaker compactness conditions C1 and C2. So basically, what we have is that our functional E satisfies the PSP condition below the level C star, and this is very well known. And C star is the well-known compactness level. So this is C star. And here's a part that's not so well known. So suppose this C is between C star and strictly smaller than 2 C star. Then if you take any PSC sequence that converges weakly but not strongly, then the weak limit belongs to the set of critical points at the reduced level C minus C star, and the distance from UN minus U to M goes to 0, or distance from un minus u to negative m goes to 0 for a renamed subsequence. In other words, un minus u either goes to m or to negative m. And moreover, if you set MC equal to the set of critical points at the reduced level C minus C star plus M, so it's the set of sums of this form with U in case C minus C star and V in M. Then this MC is contained in the complement of the origin in D, and the sets MC and negative MC can be separated by disjoint neighborhoods for small delta. So this basically verifies the conditions C1 and C2 for a problem, and then basically you apply the abstract results. So you're working in the using the spaces D1 PRN and W1 P0, and the operators AP, BP, and F are given by these formulas, and then it's easy to check that all the assumptions A1 through A2 are satisfied, and we just saw that C1 and C2 hold with these levels. This is the threshold compactness, and this B is twice the threshold. So this is basically the idea behind the proof. So thank you for your attention.